Okay, good. Okay. No. Okay, that's better. One more thing. Okay. Let's get started. Welcome back. Hopefully you had fun last week with SIMD and GPUs. Now you know how some of the most powerful processors in your pockets operate. It's amazing that we have GPUs in this, for example, and everything else we have so far. So if you thought about that 20 years ago, GPUs were not that common, really. People were thinking about having GPUs as general purpose compute engines, but no one was really having them. So you're in a different generation today. That's what's happening, I see. And everything else. Looks like my live stream wanted to talk on its own. Okay, that's what happens with too much computing power, maybe. I'm just kidding. Okay, today we're going to switch gears, and finally we're going to go to memory. I have news for you. Memory is really the most important thing when we have our computing systems. So far what you covered is very interesting, very fundamental. You have to know it, no question about that. But what we have covered so far, everything is bottlenecked by memory today. If you're running a very interesting application, clearly it has enabled a lot of things. Clearly it has been extremely successful. But today, we're having a lot of difficulties with this part, memory part. Basically, the remaining, let's say, 5 lectures, including today, are going to be on the memory technology and memory organization and how we deal with memory today. But we need to do a whole lot more in our memory and storage technologies going into the future. And hopefully this particular lecture will give you an overview of that. But I guess before we start, I want to give you another opportunity to get one more extra credit, let's say 1%. Again, this is a very simple extra credit. It's Amdahl's paper. I kind of promised that earlier. It's only a 2-page paper that talk about Amdahl's law. So everybody knows about Amdahl's law. But last time I asked how many people read Amdahl's paper. Maybe I can ask again. How many people did read Amdahl's paper? Okay, there are a couple of hands. That's great to hear. Was that after we discussed in the lecture a little bit? Okay, great. Now, if you want to get extra credit, you can actually do a review of it also. And I'd recommend doing that. It's a very fundamental paper. And it's a very fitting lecture to assign this paper because, as I said, Amdahl's law is all about bottlenecks, right? If you have a bottleneck in your system, if it occupies 50% of your execution time, if you accelerate it infinitely, the maximum speed up you will get is 2x, if the bottleneck is 50%. If the bottleneck is 90%, if you accelerate it infinitely, meaning it goes away, the maximum speed up you will get is 10x. If the bottleneck is 99% of your time, if you accelerate again infinitely, the maximum speed up you will get is 100x. So that's Amdahl's law. Bottleneck needs to be extremely large if you want to get extremely high speed ups. And memory is the big bottleneck today, not computation. Hopefully, I'll give you examples of that today. So today's lecture, we're going to talk a lot about memory. But before we go into it, these are some readings. Unfortunately, there is some about memory, and this is a bit unfortunate part also, I would say, because of the processor-centric thinking that has happened over decades and decades and decades and decades in computing. A lot of the introductory computer architecture texts kind of ignore memory, right? They don't talk about, okay, what is DRAM? You don't even learn about DRAM in some courses. You don't even learn about SSDs, in fact. We're going to talk about SSDs very briefly. But these are, I mean, if I look at this thing, this cell phone, what are you using it most for? Actually, SSDs, I would argue. SSD has enabled this thing. If there was not an SSD, a solid state drive in these things, you wouldn't be taking pictures all over the place, basically. So if you think about what has revolutionized our lives in maybe, I don't know, the last 20 years, and what has affected us so much, it's really the memory technology that goes into this, frankly. Yes, GPUs, CPUs, all of them are inside there as well. But the SSDs are what really store the data. And today we generate data and we work on data, basically. Okay, so basically what I mean to say is the book that you have doesn't cover memory a lot. So we actually have other things that we supplement things with. This is a book chapter that we had written with one of my PhD students a while ago. I think it's a very nice overview of interaction for memory systems. Okay, so let me tell you what we have done so far. Basically, we're done with a lot of things, a lot of execution models, as you can see. And hopefully you're familiar with many different processing computing paradigms. That's good. This is your food for thought. I mean, we briefly mentioned this at different lectures, but we don't have time to go into details of trade-offs of different paradigms, right? There are so many different paradigms that people have developed. What are the trade-offs? It's good to think about it. Comparative trade-offs. We talked about it in individual lectures, but it's good to have an overall view. If you really want to, let's say, build a big system going into the future, and if you really want to build it from the ground up, it's important to know these paradigms and put them in the right place, for example, or ignore some of them. Okay, another food for thought, I think, well, and also trade-offs. These different processing paradigms actually go across the stack, basically. For example, GPUs have an execution model. Algorithms can be changed to match that execution model, right? VLIW, very long instruction mode architectures have a different execution model. And again, algorithms and the languages can be changed to fit that execution model. Okay, so there's a lot to talk about here, but no time. I think it's another food for thought is what determines the adoption or widespread success of these different paradigms. I mean, there are a lot of interesting things that go in here. In addition to the technical trade-offs, there are also business trade-offs, software trade-offs, adoption trade-offs, and it's good to think about this. Like GPUs have been successful, but if you ask people that question 20 years ago, some people would say GPUs are useless. Right? Today, they cannot say that. So, but they cannot think forward also sometimes, right? So some people were quite against GPUs, let's say 20 years ago. They said, oh, what is this going to be useful for? I would call that maybe that's myopic thinking, right? They're not thinking into the future. They're thinking into maybe, I don't know, for whatever reason, they may be limited in their thinking. And as I said, this course, the purpose of this course is not really to prepare you for the exam or anything. You should be prepared for that. You know how to do that, as I mentioned, right? Do the homeworks, etc. Whatever. The biggest purpose of this course is critical thinking, such that an opportunity comes into your horizon, I don't know, 10 years down the road. You have a big computing paradigm in front of you that is sitting to be discovered, and you don't say to that, this is going to be nothing in 10 years. You evaluate it carefully, technically, and also maybe business-wise, hopefully with other things that you gather, and basically you make an informed decision about it, as opposed to let's say dogmatic or some other type of decision that may, let's say, cloud the judgment, right? And this has happened many times. I can give you an example of GPUs. Out-of-order execution processors was another example. People said, this is going to be useless. Why don't we have simple, very simple processors? Another example is SSDs, unfortunately. Flash memory. Flash memory was actually invented close to 40 years ago for at least 2 decades, 20, 25 years, it was not successful. People would basically try, almost ignore it, basically. Some people said it will never work, right? But a lot of people made it work. And I'm going to mention that, hopefully, if we get time for it today. Okay, so basically, widespread success of a paradigm, how does it become successful? It may not be immediately successful, but 10 years down the road, 20 years down the road, it can be extremely successful, right? And I've given you, I think, 3 examples of that. Okay, but let us now take a step back. So far, we've covered a lot of this computing, right? But if you think about a computing system, it's about computation, communication, storage, and memory. And this is von Neumann, his seminal paper, which we have talked about. And we don't want to cover just computing, basically, right? So recall, this is a slide that we looked at some lectures ago, I think early on. I said we're going to cover all 3 components, and now we're at memory. We covered a lot of the processing, but you have to cover processing. And we did cover memory a little bit, right? How to construct sequential logics, for example, sequential logic, and storage structures, lecture 6. So we didn't kind of ignore memory, but we almost also kind of ignored memory, right? We didn't talk about how to build caches, for example, how to build DRAM. Okay, there's also interconnects. We don't have, unfortunately, time for interconnects, but interconnects and memory are actually quite related to each other. Okay, so basically, memory is critically important. Let me motivate this a little bit, because I think it's really important to put this into perspective. I think a lot of folks, let's say, educational structures make the mistake of, it's all about computing. I would basically take a very critical step back and say, it's all about memory and memory, right? And these have to be done together, of course, right? You cannot just have memory that doesn't compute and computer that doesn't get data inside. You need to do both, right? And I think going forward, we really need to have systems that are much more tightly integrated, where you have data that's stored and you don't move it anywhere else. You just process it there. So it's important to do forward thinking. Okay, let's put this into perspective. So this is 2006. Maybe it was 2004, actually. If you look at this system, I think I've shown you this picture before. You can see that a chip, there are a lot of processing units, cores, and you know exactly how these things operate today, hopefully, at least at the architectural level. And you may be able to design it. But if you look at the chip, a lot of it is memory, right? Caches, other caches, memory controllers, memory interfaces, and there's another huge thing over there that's called main memory. And I don't even show you storage here. So let's think about where this is going, basically. Most of our systems are really dedicated to memory. And if you look at the chip itself, core, this is called the core, most of it is memory again. L1 caches, in this case, it doesn't have L2 caches, but register files, other latches, etc. Okay, this is a more recent one, 2020. You can see that. And I think we've covered a lot of things over here, right? We've covered GPUs, we've covered CPUs, we've covered basics of some of the neural engines like systolic array accelerators or SIMD accelerators. We've covered different types of cores, but a lot of it is still memory, right? You can see that there's always memory added over here. This says GPU, but a lot of it is memory. It has a huge register file in there. It has a huge scratchpad cache, etc. There's a system level cache over here. I can guarantee you there's a lot of memory over here, even though it's not disclosed. So basically, and then there's memory over here, right? And this picture does more justice to memory, let's say. So even our pictures are very processor-centric, right? We forget about this other stuff over here, even though that's what makes it work, right? There's also storage outside, which is not pictured here. Okay, old times, Intel Pentium Pro. You've seen some of these pictures, but you can see that at that time, memory was off-chip. Caches were off-chip, as you can see. Later, they became on-chip. This is Pentium 4. And this is more recent, an AMD processor. You can see that whatever I circled here is all memory. L3 caches and L2 caches. I don't even show the L1 caches. It's interesting, right? Okay, you can keep doing this. It becomes boring at some point. If you look at this accelerator chip that we talked about in some lectures, and also you saw lectures about this, basically this is the original incarnation, 18 gigabytes of on-chip memory, 9 petabytes per second memory bandwidth. It's interesting. 2 years later, 40 gigabytes of on-chip memory. So the reason why people wanted to build these chips was, if you remember, it was machine learning training, right? You want to have large amounts of computation and memory together. Okay, so the takeaway is memory system today is the most of the platform. This is my own cartoonish picture. I drew this picture in 2008 when I wrote a proposal to the National Science Foundation in the United States, saying that memory is the big problem, basically. And you can see that most of the system is memory over here. It's dedicated to storing and moving data. Yet our systems are still bottlenecked by memory. So I'm going to show you some results related to that also. Okay, so but you also seen it many times in this course, even with the computation structures that we have seen, right? For example, we said load-related stalls and pipelining, right? So you cannot have an add coming after the load because of the structure of the pipeline, right? And even with our magic one-cycle memory assumption, loads actually cause a problem. Load store handling and out-of-order execution process, we briefly talked about that. There was an optional lecture. Out-of-order execution is there to tolerate memory latencies. VLIW paradigm stalls due to long memory latency operations. And we talked about memory bank disambiguation VLIW processors, if you remember. That's all about memory, basically. How do you schedule operations in the presence of these long memory operations that are going on? Recently, we talked about SIMD processors. We talked about memory banking. We're going to talk more about it today. If you want to get one word per cycle, you'd better organize your memory nicely so that memory can give you one word per cycle, right? And this leads to banking, interleaving, which is a very fundamental concept in memory. And we gave an example of SIMD vector processor last week, where we reduced the execution time significantly by adding more memory ports, right? And you could keep doing that basically, by adding banking also. GPUs, most of a GPU is the memory actually. There's a lot of register files. If you look at the register files of a GPU, it's huge. And then there's more. Fine-grained multi-threading was there to tolerate memory latency, but even then it may not be successful in existing GPUs. So basically, you could give, these are all examples that we've covered in this particular lecture about memory, even though we did not explicitly talk about the memory system. But now let's talk about the memory system. So why are these happening? I think if you think about it generally, computing today is really bottlenecked by data. And data is really stored in memory and storage. So when I say memory, I think you should also think about storage. So important workloads are all data intensive. If you think about some workloads, machine learning, AI, genomics, data analytics, databases, graph analytics, I'll show you some examples of those also. And workloads require rapid and efficient processing of large amounts of data. And on top of this, data is increasing. And what we want to do on the data is also increasing. Basically, we can generate much more data than we can process today in many fields. I'm going to give you the example of genomics very soon as a very concrete example. But on top of that, we want to do even more sophisticated things on the data. So data is increasing, and the analysis that we want to do on the data is becoming more sophisticated. So our demands are increasing, basically. So I'd like to motivate the importance of memory in multiple perspectives. And the first perspective is really applications at the high level. What are the workloads? And if you look at some well-known workloads, a lot of these are well-known workloads, even though some of those are, let's say, it came later. Databases have been around for, I don't know, 60, 70 years more. Data center workloads came about when data centers became more popular, for example, with Google, let's say. If you look at all of these workloads, they're very much bottlenecked by memory. And there are many studies. You can actually look at these studies. You don't need to. But the summary is that memory is a bottleneck in these workloads. These workloads wait for a long time to get the data from the memory. Why memory is actually slow? It's not magic one cycle. It could be 500 cycles to access memory. It could be 1,000 cycles, processor cycles. If you think about nanoseconds, it could be 50 nanoseconds, 100 nanoseconds, 500 nanoseconds. Okay. And different aspects of memory can become a bottleneck. The latency of the memory, the bandwidth from the memory capacity can be a bottleneck. So different aspects of memory can become bottlenecks at different times. Sometimes all aspects of memory are bottlenecks, actually. For example, this graph processing, we're dealing with a lot of graphs today, large graphs. A lot of the social networks are graphs, but not just social networks. A lot of machine learning frameworks deal with large graphs. A lot of genomics architectures deal with graphs today. And if you look at graphs, there's a lot of random access that happens in graphs because whenever you do a graph traversal, you're touching a lot of different nodes distributed across memory. And these nodes are not linearly laid out inside the memory. They may be in random places in memory. So when you're traversing a graph, you may be touching a lot of different random parts of memory. You need a huge amount of memory to store the graph, and also you touch random parts. As a result, your latency becomes a bottleneck. Okay, so that's one example. If you look at the mobile end, like this cell phone executes similar applications all the time. And these workloads are also bottlenecked by memory. So TensorFlow is an inference framework, for example, that's used in cell phones. Increasingly, there would be training on the edge devices also. Clearly, we're using actually all of these right now, I would argue, because we're doing a lot of YouTube, let's say, live streaming. And while this is happening, there's a lot of encoding and decoding going on in the background right now. on the data centers and my machine as well, right? So think about it. There are some people who are watching things on the web browser right now, and there's some things that are happening that is learning about all of that behavior that's happening. So we're exercising all of these workloads right now in this class at the moment. And these workloads are also bottlenecked by memory. Okay, another workload. This is an example of genomics. Basically, today we're able to sequence genomes much better than we were able to in the past. As a result, the amount of data that we're generating is exploding, actually. This stops at 2017. I don't have a better graph, sorry. But if you look at this picture over here, we know about Moore's law, right? Moore's law says how fast is, let's say, the cost of a transistor is reducing. But the cost of sequencing a genome is reducing much faster. You can see this curve over here. And the y-axis is some cost. It's in logarithmic scale. So you get exponential reductions as you go down this way, if you're linear in this, basically. So you can see that due to the development of very high throughput sequencing technologies, we're able to sequence genomes at much lower cost today. And this is the development of more recent technologies like long read technologies. As a result, essentially, it's very easy to sequence genomes. So what does that mean? We're able to generate a lot of data. What does that mean? We need to analyze that data if we really want to do something interesting with it, right? What is interesting with it? Basically, we could do better scientific discovery. You could do better handling of pandemics. We kind of botched on that, unfortunately, but as a world. But we could still do better, basically, if we really trust science as opposed to other stuff, let's say. So basically, scientific discovery is limited by what sits in between that machine that is actually very, very able to generate data and this doctor or whoever, medical person, whatever. It could be a scientist also. But this person needs some analysis to be done on that data, and that is all computation, basically, and memory in between. So I'm not going to give you more detail than this. If you're really interested, you can read papers like this. This is a paper that we had written. So these are some genome sequencing devices. You could actually buy this device, and you could actually do your sequencing if you want. You will be bottlenecked by memory. So you could take these devices. These devices actually were shipped. Were actually very instrumental in understanding COVID-19, for example, but it could be very instrumental in everything. Unfortunately, these devices are actually very specialized for sequencing your genome, but they cannot do any processing. Basically, you really need to move the data from here to data centers or your computer and then process it. And a lot of it is bottlenecked by memory in the end. Okay, I'm not going to go a lot more into applications, but just to say that this is really an interesting field. Applications like this are really driving architecture. Right? Of course, I'm not talking about machine learning here. Machine learning is interesting, but you'll find millions of people working on machine learning to the level that it becomes very boring, right? Everybody is trying to accelerate neural networks. Okay, at least accelerate something other than neural networks as well, right? Reinforcement learning, for example. Let's get to a theory that's much more resembling true learning. And I would like you to maybe think about this critically as well. Are neural networks really true learning that we're doing today? You may be taking machine learning classes, and it's good to be critical about this, right? There are other learning paradigms that may be much more interesting to find out. So it's better not to get stuck too much on neural networks, for example. But genomics is clearly something that's also extremely interesting, and maybe we need to think about this more. Okay, so there's a lot of work that shows that this is bottlenecked by memory. And if you're really interested, there's a lot of work that builds accelerators also. So these are some example accelerators that we have built and we've been building. And you can take a look at them if you're really interested. So storage, so if you look at this, a lot of accelerators are actually placed near memory or near storage, in this particular case in storage. And this is an upcoming work that actually looks at it, again, near memory as well. But I think there's a lot more to be uncovered over here. We're just scratching the surface to really make this extremely efficient. Okay, and you can learn more about this. Okay, so that was the application workload perspective. So I didn't give you any numbers, etc. I kind of said, trust me, this is what it is. If you don't trust me, go and read the papers and do your own homework. But let me give you some numbers in terms of performance. So I'm going to give you numbers from this person. This is Dick Seitz. Remember the Alpha processor, Alpha 21264, which was the first out-of-order execution processor of its time? Dick Seitz was the chief architect of processors before that, and some processors after that also, actually. After they designed one of the fastest processors of its time in 1990s, as you can see, he wrote this one-page paper that's titled that way. It's The Memory Stupid. Basically, he says that we designed this processor extremely carefully to finish 4 instructions per cycle. It's a superscalar processor. Now you know what that means. To finish 4 instructions per cycle. But on this important workload that we designed this processor for, it's finishing 1 instruction every 4.7 cycles. Now you do the math. It's basically operating at 5% of its efficiency, right? Peak efficiency. And basically he concludes this paper saying this: I expect over the coming decades, the memory system design will be the only important design issue for microprocessors. And I think he's right, but we need to maybe make fundamental changes. Okay, 10 years later, this is my data from my first paper in my PhD. It went into my PhD thesis. We gathered this data together with Intel. And on workloads that Intel was designing their processors for, the processor on average, this is averaged across all of those workloads, most of the time the processor is waiting for data. So this red part over here is it's waiting for data to come back from memory. Okay. And if you're really interested, you can actually read our paper also. And okay, that's a shorter version. Okay, and this is the Excites paper. It's one-page paper. You can take a look at it. Okay, 10 years later, fast forward 10 years, this is data from Google. Google, you don't believe anyone in the world, everybody believes Google, right? Okay, of course, be careful, but that's kind of a, if I have to generalize it, this is probably closer to the truth than a lie. Basically, Google published this beautiful paper that shows that on their workloads, these are, according to Google, this is all of their data center workloads. And most of the time, the processor is waiting for memory. So that's what back-end bound means, according to them. If you look at this green part, that green part, this is the top of the line Intel processor of its time. The processor is finishing instructions, retiring instructions only in that green portion. So 10 to 20% of the time, you can see. Okay. And there's a lot more analysis over here, as you can see over here. So there's a lot more, but if you really want to learn more about this, there are a lot of interviews, etc. you can find. It's actually interesting. Okay, that's performance. Performance is bad. Energy is even worse. So basically, we're wasting performance. We're wasting a lot more energy. And today, I think we should really be caring about a lot more energy, perhaps, because that's the key to sustainability, right? So if you look at this picture, this is, again, old data borrowed from Bill Daly's presentation. You can see that this is actually, Bill Daly is the chief scientist of NVIDIA, if you didn't know. But basically, this shows that a complex arithmetic operation, double precision floating point operation, consumes 20 picojoules. A DRAM read or write, memory read or write, consumes 800x the energy of that. You look at the field, there's usually a memory access is much more expensive in terms of energy than computation, a DRAM access. So this 2 or 3 orders of magnitude, as you can see, right? Now, maybe I'll take some time over here because we talked about Moore's law and technology scaling, right? If you go back 70 years ago, this is when von Neumann was designing his architectures, etc., right? This was expensive. This was very expensive, actually, and this was cheaper, relatively. So we had 70 years of technology scaling where we were able to make computation much faster because we reduced the size of the transistors, we made them much more efficient, and we made them faster. As a result, computation became extremely cheap in terms of both performance and energy and cost, all of them. Unfortunately, memory stayed. It didn't improve as much, let's say. Why? Because it's bottlenecked by interconnects overall, and also the memory technology. And these did not scale very well because interconnects are harder to scale, actually, if you look at the transistors. People are focused on transistor scaling. They were able to reduce it. But interconnects are very fundamental. It's a wire, basically. How do you make that much more efficient and much faster is much more difficult than the computation unit that you have, that you build with logic. Okay, now we'll go beyond the abstraction level of this course, so I don't want to do that. But that's the reason why memory became a huge bottleneck today. If you go back 10 years ago, it's less of a bottleneck. If you go back 10 years ago, less of a bottleneck. But it's becoming a bigger and bigger bottleneck over time. Okay, so this is another interesting comparison point. If you look at a very simple operation is actually much cheaper. This is a simple integer operation, 32-bit addition, basically. And a memory access consumes 6,400 times the energy of that integer addition. This is just to put things in perspective. So later in this lecture, we're going to look at SRAM, for example. It's also energy efficient comparatively. But the memory access, because it's dominated by these huge interconnects to go to memory, is energy inefficient. And you will see later that we're actually trying hard to reduce the interconnects. But because there's so much memory out there that we need more memory to store the data, it's very difficult to reduce the length of those interconnects. And you need to go through a lot of interconnects, basically. Okay, wires. You can think of it that way. Wires are interconnects. Okay, if there's a lot more data, actually. This is in this paper, as you can see. There are a lot of comparisons of why memory is a bottleneck. I think I mentioned this paper that we wrote with Google a few years ago. And basically, this paper shows at a system level that memory is consuming most of the energy. On these workloads that I showed you that we're exercising today, like YouTube workloads, Chrome browser, inference engines, more than 60% of the entire system energy is spent on moving data across the memory hierarchy. Not doing computation, just moving data. Okay, and that's why we actually have been proposing in-memory computation. If you really want to know about an informal article, there's on ETH webpage. We're not going to talk about future paradigms as much, unfortunately. We don't have time in this course. We talk about them a lot in the master's level computer architecture course. But going forward, we should really think about changing the paradigm to something else. And if you really want to know about that, either take the architecture course or there are a lot of tutorials we put up online. Okay, so this was, we talked about applications, performance, energy, and let me finish up with the reliability and security perspective. This is not going to be, this is going to be familiar to you because we talked about RowHammer, for example, but this kind of issues are going to get worse. Basically, memory is a big source of unreliability in our systems also. I mentioned that multiple times, but this is one work that we did with Facebook some number of years ago, where we showed that there's a very strong correlation between this is all of the production data centers that Facebook operates at that time, of course, right? And this is huge. A lot of memory, a lot of data. You can see that the chip density correlates strongly with the server failure rate. As chips become denser, server failure rate increases. Why? Memory is less reliable. As memory capacity increases, cells become smaller, cells become closer to each other, memory cells. As a result, you get data corruption much more easily on those cells. And once data corrupts, your system fails. Why? Because your server crashes, for example, your server hangs, or you get some uncorrectable errors that you figure out after some point and you try to correct. Sometimes you have silent data corruption that you cannot even correct, right? You don't even know sometimes that something went wrong. Maybe down the road, 1 month later, you figure that out. Maybe you don't even figure that out, right? Maybe you get corruption, you get wrong results. It happens, basically. And this is because memory is a large component and there's a lot of reliability issues over there. Okay, so that's reliability. And if you're interested, there are a lot of works that talk about this. We talk about RowHammer, so I'm not going to talk about it in detail. Clearly, it's a security problem also because people can induce bit flips in a predictable way in DRAM today. This should not happen, clearly. And one can take over an otherwise secure system. We talk about this, that's why I'm going through this relatively quickly. And if you're really interested in knowing more about RowHammer, this covers basically research that has happened in security, architecture, systems, circuits, and devices. So this is really a problem that spans across the stack. There are people working on it at the device level, as well as software security level, which is really interesting. There are not that many problems that people work on that way. And this paper covers a lot of the work in that area. Okay, so you know about this hopefully by now. And this is actually a talk that I gave recently, and where I summarized 10 years of RowHammer research in 20 minutes. I hope I won't be able to. I won't summarize it 10 years down the road. I hope people fix this problem. My feeling is it's going to be very difficult. Okay. Basically, I think hopefully this shows you that memory is really critical for computing. Everything we built cannot work without memory, and maybe we should be focusing a lot more on memory going into the future. So I did not talk about some other aspects over here, right? Clearly, I kind of motivate this. Cost is also important. If you look at a data center today, most of the cost of a server comes from memory and storage, actually. More than 65% of the cost comes from memory and storage. Processors are expensive, no question about that. But you get so much memory and so much storage that's a lot more expensive. Form factor of this is limited by a lot by memory and SSDs, and quality of service and predictability, right? Because there are a lot of things that are accessing memory. So predictability of performance becomes a problem also. Quality of service that different applications get becomes a problem. So with that backdrop, let's go into memory fundamentals. And we're going to start with memory organization and technology. Memory organization is interesting because a lot of memory is organized independently of technology. A lot of memory is organized similarly. So there are some fundamentals in memory organization. If you look at memory organization, you start with a cell. You build an array out of that cell. You build some sensing structures to sense from the array. and then you replicate those arrays, and then you replicate to form some module, and you replicate the modules, and then you replicate more modules, basically. That's kind of how I think of memory organization. You start with a cell and then build arrays and arrays of arrays, let's say. And all memory is designed this way. And the reason is really to cope with the huge capacity that you need while having reasonable latency, let's say. Okay, but let's start from the top level perspective, programmer's perspective. From a programmer's perspective, memory looks like this, right? You do loads and stores to it. At least programmer who's taking digital design and computer architecture, right? Some people don't even think about loads and stores if they program in Python, for example. They don't even know what a load is. That's a bit unfortunate, but you guys are going to be computer scientists, so you should probably know what a load is, right? How things operate underneath. Well, you know what a load is. But let me distinguish between two things first. What the programmer sees is virtual memory, actually, in many systems today. Actually, in most systems today. We're going to get back to virtual memory. The reason is programmer can assume memory is infinite. So virtual memory provides this nice illusion to the programmer so that the programmer doesn't need to deal with running out of memory. I don't have enough physical memory. My physical memory is, I don't know, 4 gigabytes. What if my data is 1 terabyte? Should the programmer really deal with this? Should the programmer really manage the physical resource? In the past, they did, but after virtual memory developed, people do not need to manage it. So this improves productivity significantly. So in reality, physical memory size is much smaller than what the programmer assumes, right? And the system software and hardware, cooperatively, map virtual memory addresses to physical memory. So there's some translation layer, there's some indirection that happens. And the system automatically manages the physical memory space transparently to the program. So programmer assumes nice, I don't know, 1 terabyte or even bigger virtual memory space specified by the ISA, but physical memory can be much smaller. So we will go into how this operates, hopefully in next week, not next week, but the week after, last week, basically. The big advantage of this is that programmer doesn't need to know the physical size of the memory, nor do they need to manage it. That's beautiful, right? Like, you don't need to manage, for example, your physical memory, DRAM, as a programmer. And a small physical memory can appear as a huge one to the programmer, and life is easier for the programmer. And this is one of the most successful ideas from the 1960s also. But of course, the downside is there's more complex system, both software and the architecture. And we're going to see that complexity. Unfortunately, this is becoming extremely complex actually today, in my opinion, especially when physical memory sizes grow. For this layer, virtual memory layer to manage memory is becoming very difficult. But this is another classic example of programmer microarchitecture trade-off. To make programmers' life easier, microarchitect and the system designer, their life becomes harder, right? Now they need to manage the virtual to physical memory translation. Okay, so we're going to talk more about this. Think about it, maybe in your free time. How many have you guys seen virtual memory before? Okay, so you haven't taken a course yet. You will see more of it when you take the systems programming course. If you've taken systems programming, probably you've seen it. Okay, but we're going to talk about the physical memory system today first, before we build an abstraction on top of it. Essentially, you need a larger level of storage to manage a small amount of physical memory automatically. And physical memory has a backing store. That's the disk, actually. That's an SSD, for example. In fact, part of your physical memory can be the backing store for your physical memory, and then you can have the SSD. So think about the memory system as not just your, so your caches exist, of course, we're going to talk about that, and then your main memory, and then there's the SSD that sits. And then there could be a tape or something else out there as well. But we will first start with the physical memory system today, or now ignore the virtual to physical indirection. And we will get back to it later. Not today, hopefully in a couple of weeks. But let's talk about, before we go into details of the physical memory system, let's think about idealism first. What do we want from this memory system, right? So we covered a lot of the pipeline, right? Instruction execution. And ideally, if I have to specify what I want from this pipeline, I want no stalls, right? We tried very hard to eliminate stalls, but ideally we want no stalls, perfect data flow, zero cycle communication, enough functional units, and zero latency computation. Of course, we cannot get that, but we try to approximate it as much as possible, right? Instruction supply, we covered that a lot also, right? Ideally, we want zero latency access. This is part of the memory system also. Part of the computation also, because you supply instructions, because we covered the branch prediction, for example. Beyond perfect control flow, we covered branch prediction a lot over here. And ideally, we want infinite capacity and zero cost. Yes, instruction supply is interesting, but today we don't have huge programs, right? Programs can be large, yes, but they're not in the order of terabytes. So what is really interesting in the main memory is really data supply, I would argue. Here, perfect control flow is extremely interesting. That's why I think of instruction supply very tightly integrated into the compute engine, right? Instructions are not huge in terms of capacity, but perfect control flow is extremely important. Whereas data supply, you need this data so that you can continue the processing, right? So zero latency access, infinite capacity, infinite bandwidth, and zero cost. Those are the ideals that we want to achieve. I'm going to mention this later on tomorrow when we talk about the memory hierarchy also. Again, this idealism is what drives us to make some decisions. Of course, we're not going to be perfectly ideal, right? Because this is, I mean, unachievable, right? How do you achieve zero cost and all of the other things on top of that? Okay, so as I said, main memory consists of arrays. So let's talk about these arrays. Let me give you a quick overview first, and then we're going to build up and down. So what do you build arrays from, right? This is what brings us to the memory technology. So memory technology can have different things, can be built of different storage technologies internally. And when we first introduced storage elements in this class in lecture 6, we talked about flip-flops, right? Or latches. We first talk about latches, and then we build flip-flops. All technologies have trade-offs, basically. This is, we're going to cover some high-level trade-offs first. So if you look at the flip-flops, we wanted them to be very fast, and we wanted them to be parallel access. And that's the upside of them. And they're very expensive as a result of this. If you remember, gated D latch consists of tens of transistors, right? I think it was more than 40 transistors. So their cost is very high, basically. But they give you very fast access and parallel access. So you know how to build these today, hopefully. Now you could build terabytes and terabytes of flip-flops. Unfortunately, that's not going to be very cost effective. You don't want terabytes and terabytes of 40 transistors per bit, right? That's a lot. So people actually built memory with other technologies. Static RAM, we will describe them more in a moment soon. These are relatively fast. They have some restrictions, as we will see, but they're expensive. They're less expensive compared to flip-flops, but they're still expensive, I would argue. So 1 bit costs about 6+ transistors. So if you remember the cross-coupled inverter, I said that we're going to see it, and I mentioned that SRAM at that point in lecture 6. This is built of cross-coupled inverters, 2 inverters feeding each other, and then you have 2 other access transistors to actually have access. There are variants of it that are 8 transistors, etc., but you don't need to worry about them. But the takeaway is that this is fast and expensive, but not as fast as flip-flops and not as expensive as flip-flops. Again, you can build main memory with this, but this is going to be very expensive. So people have invented dynamic RAM in 1960s. It was at IBM, actually. I just gave a talk at IBM early this week, actually, on RowHammer and memory technology. So we had a lot of lively discussion on dynamic RAM. But basically, dynamic RAM, let's talk about the advantage. It's cheap. 1 bit is only 1 transistor and 1 capacitor. So we're going to see that actually very soon. You can see that the cost is immediately much less than static RAM. Unfortunately, there's a lot of downsides also, like slower, you get 1 word at a time, reading destroys content, we talked about refresh, and needs special process for manufacturing. So we're going to cover some of these trade-offs later on today. But this is how we build main memories with today, because this technology is cheap enough to store huge amounts of data. Unfortunately, it's not cheap enough to store even huger amounts of data. It's cheap enough for what you can fit in, I don't know, 1 terabyte, let's say. But if you need tens of terabytes, exabytes, petabytes, whatever it is, you don't want to store it in DRAM today. You need some other storage technology that's actually even cheaper. But of course, even cheaper, like flash memory, hard disk, or tape, that's even cheaper. 1 transistor stores many bits, actually. For example, in today's flash memory technologies, in 1 transistor, you can store 4 bits. Because you take advantage of the levels of voltage that exists in the voltage range of the transistor, a special transistor, of course. It's called a floating gate transistor or charge trap transistor. But of course, the downside is it's much slower and access takes a long time. The other advantage is non-volatile. So all of these three technologies over here are volatile, meaning whenever you turn off the power, they lose their data, whereas the storage technology is non-volatile. Okay, so hopefully you get the idea over here, right? There's a big trade-off between, in terms of technology, there's a trade-off between cost and latency. And this is a very fundamental trade-off. Different technologies land at different places in that cost-latency trade-off. As a result, it dictates how we build our memory systems, right? We use SRAMs for fast caches. We use flip-flops for register files, for example, or pipeline registers. We use SRAMs for caches. We use DRAM for main memory, and we use other storage technology for our storage systems, basically. But regardless of the technology, you build arrays in the end. So everything is organized in terms of arrays. So the goal is to really efficiently store large amounts of data. And if you look at any of those technologies, you give them an address and you get some data bits. M-bit address, you get some M-bit data. Of course, some part of it is configurable, right? Sometimes you may be able to get, let's say, different granularities of data also. But we'll look at one granularity. And internally, this array consists of the different storage technologies. There could be some difference, of course, internally, but externally, it looks like this. So basically, you have a memory array that stores data, address selection logic that selects one row of the array, and there's some readout circuitry that reads the data out. Now, not just reads the data out, but also senses what the data is, tries to maybe correct the data if it's wrong, etc. So there could be some other things that are inside this array that we're not going to talk about. So even though it looks kind of simple, it doesn't mean that this array is not easy is not difficult to build. It could be very difficult to build this array actually. But okay, the abstraction is that an M-bit value can be read or written at each unique N-bit address. So all values can be accessed, but only M-bits at a time. So there's some access restriction that allows more compact organization as well. So recall that we had a memory array, right? This was our memory array. We called it a bigger memory array at that time because we actually made it bigger compared to a smaller memory array. And this was our we have 4 rows here and 3 columns. And we were able to address 4 rows. So address bits are 2 bits. And each location gives you 3 bits, right? If you really want to get 1 bit, you could have another multiplexer here that multiplexes between the 3 columns, right? So you could actually give it a 4-bit address for rows, 2-bit address for rows, and 2-bit address to distinguish between these 3 bits for the columns. And then another multiplexer down here, which doesn't exist in this picture, of course, can multiplex between these bits so that you get 1 bit out as opposed to 3 bits, right? So basically, you could play tricks in the peripheral circuitry to get the number of bits that you want out. And we will see that this is going to be useful later on. Okay, so this was our bigger memory array. So if you abstract that bigger memory array, it looks like this, right? We have 2 bits of address, and we get 3 bits of data because each address stores 3 bits of data. That's our abstraction for what we saw in lecture 6. Actually, I showed you in lecture 7 as well. And this is what the memory looks like, right? One example. So basically, we have a 2-dimensional array of bit cells. Each bit cell, so each bit cell is this one. In this particular case, it's made of D flip-flops, as you can see. It could be made of SRAM. It could be made of DRAM. It could be made of flash. It could be made of magnetic material. But I think it's clear that you have 2 of the N rows and M columns, and depth is the number of rows, width is the number of columns, basically. I mean, I have some things about words over here, but you can ignore that. It's not that important. And array size is really the depth times width. So it's 2 to the n times n. Okay. Now, as n and m grows, it becomes difficult to build this array as a single array. That's the key point over here. So I think I've already said this, so you can do this example yourself. So if you want to make it bigger and wider, you grow n and m, right? In this case, n became 10 and m became 32, right? Okay, this is still small, right? We're talking about terabytes. For terabytes, your n and m need to grow to, I don't know, to the 40. This should be like 48, 50, maybe 60. And this should be something big also. Okay, we're going to get back to that. So if you look at the memory array, storage nodes, so each node is called a storage node or a bit cell. There are multiple words for it. You have a column over here, and in each column, storage nodes are connected to the bit line. We've also seen this one in one of the lectures earlier. And you have an address decoder over here. An address decoder activates only one word line. Depending on the address you see, one word line is activated. And activation of a word line means that the storage nodes on that word line get connected to their respective bit lines. So this gets connected to this gets connected to this gets connected to this. If the address is 0, 0, as a result, you read the words in these 3 storage nodes in the bit lines. So this example shows the address 10, which I've already set for this one. So basically, you have this word line plus bit line structure, 2-dimensional array. And this is the first thing is called an activation. And you basically activate a word line, which brings you all the data in that particular row. Right? And this is, again, independent of technology. We're talking about independent of technology. This could be a flip-flop. This could be DRAM. This could be potentially an SSD. OK. So how is access control? Let's talk about the technology element. So you have basically access transistors that are configured as switches. We saw the transistor as a switch in the earliest part of this lecture, right? This course. You configure these access transistors, and they connect the bit storage to the bit line. So basically, you have some access transistor that's not shown here, but it's shown here. So you have an access transistor. In DRAM, you have a capacitor over here. And whenever you activate the word line, this capacitor gets connected to the bit line, and you sense the charge in the capacitor. In SRAM looks like this. It's a cross-coupled inverter. You have 2 access transistors. You read the value and the complement of the value on both sides. And then there's a sensing structure. So when you actually activate the word line, bit line bar contains the, let's say, value bar, and bit line contains the value. And there's some sensing structure, which is not shown here, that senses what the value is. And having the value and value bar is very useful for that sensing structure because you can make it faster. Okay? In DRAM, you don't have that luxury. You don't have, because the cross-coupled inverter stores both the value and the complement of it, you can design your sensing structure to be extremely fast by looking at both and do what's called differential sensing today. Whereas in DRAM, you don't have that luxury, let's say. And that's only one of the reasons why this is slower on the left. So I gave you some differences between the technologies right now, right, because of how they're built. Okay. So building larger memories requires larger memory arrays, right? And large means slow in general because you have longer wires. So these are wires, right? Let's go back over here. You have longer word lines if you want to increase the array's number of columns. You have longer bit lines if you want to increase the number of rows. You have bigger address decoders, and you may have bigger multiplexers, which we didn't talk about right now, but we're going to talk about a bit later. And you have bigger sense amplification structures. So everything becomes bigger. That's why large is slow. So the question is that we're going to talk about in the remaining part of this today is how do we make the memory large without making it too slow? It's going to be, so if I tell you that you're going to make memory large and you're not going to make it slow, you should kick me out of this room because that's very fundamental. You're not going to make a memory that's larger and the same speed. I'm not talking about larger by 1.1x, right? I'm talking about larger by 10,000x, let's say. Okay, so the key idea we're going to look at is we're going to divide the memory array into smaller arrays and interconnect the arrays to input and output buses. So large memories are essentially hierarchical array structures. You can think of it that way. You look at an array. Internally, it's an array. It's two-dimensional arrays. Inside it, you look at it. It's maybe two-dimensional or one-dimensional arrays. So basically, you keep building arrays of arrays. So we're going to see it in DRAM soon. It's a 5-dimensional, maybe even more structure. You have channels consisting of ranks. Ranks consist of banks. Banks consist of subarrays. Subarrays consist of mats. Mats consist of cells in the end. Okay, so this is a good place to stop and take a 10-minute break. We're going to continue building memories. Okay, let's be back 2 or 3 minutes after the bell rings. Hello.
I have a question concerning instruction memory and the instruction fetching, and you said you
Okay.
sort of quickly passed over it and said that this, I mean, total instructions are a lot of stuff, but still.
In terms of size, it's not as big as data, basically.
But doesn't it still? I mean, there is this whole problem with branch prediction. And stuff.
Yeah, sure. Branch prediction becomes that much worse. Yes.
It's hugely exacerbated if you have memory access.
Yes, absolutely,
like,
absolutely.
I don't know, 20 or 50 cycles.
Absolutely, yeah. I should talk about that. Yes.
Like fetch 50 cycles ahead.
Exactly.
Doesn't this like?
Exactly. Yeah, maybe I talked about it in the wrong way. So branch prediction problem, absolutely, it gets exacerbated with the memory latency.
If the pipeline is like 20 stages long and it takes you 50 cycles to access memory, it more than doubles.
Absolutely, yes. Yeah, absolutely. Pipeline becomes much worse with longer memory access. All right, let's get started. Before I continue, let's see, where is the slide? Okay. Okay, before I continue, I want to, let's say, correct one potential misunderstanding. Because one of your students, fellow students, came up to me and he's absolutely right. I did not mean that this is not important. This is extremely important. What I tried to say over there was that the size of the instruction memory doesn't need to be as large as the size of the data memory, let's say, data supply. Today, we're dealing with huge amounts of data, whereas instructions are not growing as fast as the size of the data. But this is still extremely important for performance, because if that memory is extremely slow, you know what's going to happen is that you're not going to have perfect supply of instruction to the pipeline, right? If you get a branch misprediction, for example, and it resolves in 500 cycles because you need to wait for a memory access to resolve the branch prediction, you're not going to be able to fill your pipeline for, I don't know, hundreds of cycles, right? So basically, this instruction supply, the memory over here, is greatly affects how fast you can supply instructions to your pipeline. And if you don't supply instructions to your pipeline, you're not going to be able to even access data, right? The first step is to get the instructions to the pipeline, right? Okay, so that's the point over here. So what goes on in the instruction supply is still extremely important, but the size of it doesn't need to be as large as the size of the data supply. Okay, so we had to correct that. Now let's get back to where we are. So we were in this slide. So we were going to build larger memories. And the key idea is divide the memory into smaller arrays. Because if you want to build a huge memory as a large array, everything becomes bigger, interconnects becomes extremely long, decoders become huge. So your latency is really increased greatly. It's a better approach to use the divide and conquer approach, right? Divide and conquer is also fundamentally, very fundamental, clearly, in a lot of aspects of life, in addition to algorithms. So we're going to divide and conquer as well. And in case of DRAM, you have a multi-dimensional array structure, as we will see. But the general principle is based on what's called banking. And we've already seen banking, right? When we talked about single instruction, multiple data engines, vector processors, and memory access, we talked about banks. Why? We wanted to supply one word per cycle into the processor, right? Why? We want to actually get a huge array of words, right? Vector of words. So we've already seen banking. So banking achieves multiple purposes. One purpose is to increase throughput so that you can get enough number of words per cycle. And the second idea is to reduce latency with reasonable cost, increase the size of your memory. Okay, but basically the problem it's solving is a single monolithic large memory array takes long to access and does not enable multiple access in parallel. Now the second part you can solve by adding more ports. You can have, let's say, if you want to access 1,000 elements, you can add 1,000 ports to a single memory array. Unfortunately, this is also extremely expensive. So what is a port? So if you go back over here, so here you have one word line that's connected to this DRAM cell. Instead of being able to activate one of them, have a way of activating many word lines at the same time. You need to replicate the decoders, row decoders, for example, to be able to do that. So if you go back over here, you need to replicate the row decoders to be able to do that and add some other structures. So you can have thousands of them potentially, but that's extremely expensive. So it's much better to divide the array into multiple components to reduce the latency of the memory array access and enable multiple access in parallel. So you kill, again, two birds with one stone. And the idea, I already said this basically, divide the large array into multiple banks that can be accessed independently. Independently can be thought of in space and time. You've seen the space and time duality in array versus vector process. It's a similar idea over here. Either you can bank memory such that you can independently access all of them in the same cycle. Right away, you get the data out in the same cycle also. Or you can independently start accesses in consecutive cycles, right? Again, cost is what determines what you do over here. But the key idea is divide the memory into multiple banks so that you can access them independently, either in the same cycle or in consecutive cycles. And this enables you to make each bank smaller than the entire memory storage, and accesses to different banks can be overlapped, either completely or mostly or partially, depending on when you start the multiple accesses, right? So of course, as we also discussed in the SIMD and GPU lectures, a key issue is how do you map data to different banks in all of these? Right, in other words, how do you interleave data across banks? And we've discussed that in the lectures, and there are beautiful papers that are written. People are still trying to figure out how to map data nicely across banks so that you minimize the conflicts. Because you can have two accesses, you can do two accesses in parallel or mostly overlapped if data that you need is in different banks, right? If the data that you need for two different accesses is in the same bank and you need both of the data at the same time, then you have a bank conflict, and this requires to serialize the accesses, right? So mapping of the data makes a big difference. And since we already discussed this, I'm not going to go through this in a lot of detail, but remember that this was a slide that Juan showed. You can see that the memory is divided into banks, and banks can be accessed independently. In this particular case, banks share the address and data buses. It doesn't need to be that way. Banks can be completely independent also. In DRAM, and this was DRAM in that particular case, even though it was not said, having concurrent data buses and address buses is expensive because DRAM usually is on a different chip. And on a different chip, that's very cost sensitive. If you actually have, let's say, 100 banks, we talked about 16 at that time. Okay, let's do 16. If you have 16 banks, each of them can take a 32-bit address. Each of them can supply a 32-bit data. That's a lot of pins per chip. That's 64 pins per chip, per bank. And if you have 16 of them, 16 times 64 is a lot also, right? It's 1,024. So you need 1,024 pins out of your DRAM chip. And that's very expensive, basically. So normally what happens in DRAM chips is you have multiple banks, but they share the address and command buses and the data bus such that you can only start one access in a bank at a time. If you want to start another access in another bank, you do it in the next cycle. And you get the data in an interleaved fashion on the data bus, not concurrently from different banks, but in a pipeline manner in different banks in consecutive cycles. So you can see now that cost trade-offs are dictating what we kind of build in terms of our banking. Right? Banks cannot be completely independent of each other because cost is very high if you make them completely independent of each other, because every data and address bus in DRAM requires a pin if you make them completely independent of each other. Now in SRAM technology, these banks can be completely independent of each other today in our processor chips, because in a processor chip SRAM, you build caches out of SRAM, and those caches don't require extra pins because they're on the same chip as the processor. As a result, you're just using wires internally in the chip. There's nothing external that gets communicated. So banks in an L1 cache, L2 cache, for example, L3 cache can be completely independent of each other. So depending on where you build the memory also dictates the trade-offs, as you can see. Now let me give you the generalized memory structure. I'm going to focus a lot on DRAM here because we're going to see SRAM later on. But basically, you start with cells. Basically, you have multiple rows of cells and columns of cells, and a two-dimensional array gives you a bank, essentially. And each intersection in this matrix, each cell in this matrix basically gives you one DRAM cell, which consists of a capacitor and an excess transistor, as we showed earlier. So a cache line can be consisting of 4 of these columns, 4 bits in this particular case. Of course, this is not realistic, but imagine a cache line being 64 bytes. That's also possible. So in this particular case, that's your bank, basically. It's a two-dimensional array. And then you have 4 of these banks inside it in this particular DRAM chip and some peripheral circuitry. That's your second level. And you have 4 of these chips inside a single rank of chips. That's called a rank in DRAM. And then you have 4 of these ranks in a channel. And then you have 2 channels in this particular case, controlled by different memory controllers. So you can see that we started with this array. We built an array of those arrays. We built another array of those arrays, and we built another array of those arrays. and then we built another array of those arrays. So that's n-dimensional, as you can see. You could keep doing this basically. Okay, it's fun. Of course, you need to have some peripheral circuitry, etc., to make it work as well. So this is another picture over here from some of our papers. If you're really interested, you can take a look at the background sections of these papers. But it shows essentially the same thing in a different way, right? Okay, so just a quick thought about cutting edge. So this is two-dimensional. So if you look at these banks, they're two-dimensional. Everything is laid out in two-dimensional. But you could also go three-dimensional today, meaning you could essentially have banks inside a layer, and then put multiple layers together, such that you could keep increasing the memory size in the third dimension, let's say z dimension. Pick whatever your choice is. And today people can build things like this. We don't have time to talk about it, but basically you can build many layers of memory on top of each other so that things can get better stacked. Things can be even denser that way. You can also build some logic layer underneath so that you can have controllers, for example, underneath. And it turns out this logic layer can have very fast or reasonably fast and high bandwidth access to these memory layers. So you have many, many connections over here. And then you can have, this could be your chip basically, right? Memory chip. There's some technology called high bandwidth memory technology. You may have heard of it. Modern GPUs use it. Today it's extremely expensive, but it's basically operating using these principles. It's three-dimensional stacking, and it has these memory layers and the logic layers. And as a result, you get extremely high bandwidth to the logic layer, and also outside the chip a little bit. And that's why GPUs actually use it so that they can get extremely high bandwidth. Because remember, GPUs are SIMD processors, and they need high bandwidth so that they can process huge amounts of arrays, right? Okay, so let me give you the top-down view of DRAM. I kind of given you it, but let's break it down into components in a little bit more. We start with, let's say, a real processor. It doesn't matter, it doesn't have to be Intel. But I've kind of giving you the channels, right? There are 2 channels in this processor. In modern processors, there could be 4 channels, even more channels in some processors. Basically, a memory controller controls one of the channels. And inside a channel, you can have multiple DIMMs. It's called a DIMM. We're not going to go into the history of why it's named that way, but it's called a dual inline memory module. And you can see that this is a memory module over here. We have 4 memory modules in this particular case. Let's take a look at one of the memory modules. So memory modules can have, they have a front and a back. This is what you insert into your motherboard, for example. And you have basically, in this particular case, you have 8 chips on one side and 8 chips on the other side. So the different sides are called ranks in this particular case. And you may actually have some other chips. This is called a serial presence detect chip that has some amount of non-volatile memory in it. And memory controller, when the system is getting set up, talks with that SPD chip and learns about what kind of memory is there, for example. You could store more information over there, actually, potentially, so that memory controller knows about what it's dealing. So as I said, you have 2 ranks in this particular case. Rank 0, each rank is a collection of 8 chips. And the reason it's called a rank is, it's like a rank of soldiers, right? Whenever you give a command to a rank of soldiers, they do essentially the same thing, but they do it with different elements. I mean, for example, they raise their hand this way, right? All of them. But they're different hands, right? So that's the idea over here also. You send the memory controller sends a command to the rank of chips. The chips do exactly the same thing, except they give different data, or they write different data, or they give you different data. That's the idea. So this is what a rank looks like today, multiple ranks. Multiple ranks share the address and command buses. And there's a chip, essentially rank select signals or chip select signals. They also share the data bus. So in many of today's systems, ranks cannot be accessed concurrently. They're there to increase the capacity of memory. But you access only chips from only one rank at a time. And then you switch to the other rank if you need to access something from that rank. And the reason it's built this way is, again, to save cost, right? If you look at this DIMM, there are only one set of pins to serve one rank at a time. If you want to serve 2 ranks at a time, you need to increase the pins. Again, cost. As you add more pins, input, output, drivers, interconnects, the cost increases. Okay, feel free to ask any questions. Okay, now we're going to focus on our ranks. So inside each rank, So what does rank give you? Each rank gives you capacity, right? You could actually, you have, for example, in this case, you have 8 chips. You have 2 ranks. Now you have capacity of 16 DRAM chips. Right? That's how you build larger and larger capacity memories. And if you go back, let's say each channel gives you capacity also. If you have thousands of channels in your processor, you would have a lot of capacity. But unfortunately, each channel consumes pins in the processor side as well as the memory side. Okay. So if you go inside a rank, it consists of 8 chips in this particular case. Each chip provides 8 bits in this particular case. So the interface of a chip, DRAM chip, is very small, as you can see. 8 bits is, so there are some DRAM chips that can provide 4 bits. There are some DRAM chips that can provide 32 or even 64 bits. The larger the interface is, the more expensive the DRAM chip is usually because it's cost again. In this particular case, many DRAM chips provide 8 bits at a time, as you can see. And you put 8 chips together such that you can get 8 times 8 bits, meaning 64 bits. Right? So basically, you can concurrently access all of those chips and get 64 bits at a time. So why do we have multiple chips concurrently accessed in a rank? So what does this enable us? That gives us higher bandwidth, as you can see. You get larger data words, or you get larger words at a time. Instead of just getting 8 bits at a time, you get 64 bits at a time. You also get higher capacity. So it gives you multiple things to connect, not connect, essentially put together multiple chips and essentially control them at the same time. Okay, so that was our rank. Now, inside each chip, I said that each rank in this particular case has 8 chips. Inside each chip, we're back to the banks. Now we're going down. We have 8 banks in this particular case. In modern DRAM, it could be 16. It could be 4. Today, it's mainly 16, actually. But there are some really idiosyncrasies also. Some banks cannot be accessed completely in parallel, etc. So there are actually interesting things. But banks are essentially what we saw earlier. Each bank gives you 8 bits at a time. But they share address, data, and command buses. So you can start access from a bank every consecutive cycle, in consecutive cycles. So you get the data out in consecutive cycles as well. Right. That's the trade-off that people have made in DRAM because DRAM chip is not wide in terms of the data that it can provide. DRAM is extremely cost sensitive. Okay, so if you break down a bank, let's focus on one of these components, one of these arrays. A bank looks like a 2-dimensional array of cells that I mentioned. Basically, in this particular case, there are 32,000 rows and let's say 2,000 times 8-bit columns, right? 16,000 columns. In this case, we talk about a column as 1 byte. So you can think about 2,000 columns. So these arrays are usually people try to make it rectangular to maximize yield and minimize latency issues, right? Otherwise, one latency is larger than the other, etc. So the design of these arrays are actually both science and art in the end. Okay, so 2-dimensional array of cells. When you access one row, you activate the word line of that row, and it gets brought into what's called a row buffer in DRAM. This is an array of sense amplifiers, essentially, or a row of sense amplifiers. There's a sense amplification mechanism that amplifies the charge, figures out whether the capacitor stores a 1 or 0, and then supplies the data out. And you can see that there's a multiplexer at the end after the sense amplification, after the row buffer. So after you activate one row, the data gets brought into this row buffer, and you access that row buffer with a column address to get the column that you want out of which 1 byte you want out of the 2 kilobytes over here, basically. You know about multiplexers by now, of course. Okay, let me give you the high-level perspective of the DRAM bank operation. So you have columns and rows, and this is an abstraction. Internally, a bank consists of many cells, transistors, and capacitors, and other structures that enable access to the cells. I'm not going to show you exactly how it operates. If you want to know how it operates, I'm going to mention some later lectures. You can also take the computer architecture course, as we discussed. But basically, at a high-level perspective, you need to first bring the row into what's called a row buffer, sense amplifiers. And initially, this is empty. Let's say memory controller accesses an address in row 0, column 0. It first needs to supply the row address. It goes through a row decoder and activates one row. Okay, so it first needs to issue an activate command. Activating a row means applying high voltage to that word line, enabling that word line, which brings the data into the row buffer. It's sensed right now and amplified. Nice. Now you can read it from the row buffer. The memory controller supplies a column address. And that column address gets multiplexed out of the row buffer by the DRAM chip and sent back to the memory controller. Okay, so there's a row address and column address. Even those are sent separately by the memory controller. So DRAM chip is so cost sensitive that you cannot send the entire address, row plus column, in one cycle, because that consumes more pins, right? Imagine row address being, I don't know, 14 bits and column address being 14 bits also. You don't have, you want to minimize cost, so instead of sending 28 bits at a time, you send 14 bits at a time in consecutive cycles. Okay, that's the idea. So that's how cost sensitive DRAM is. We want to, why? Because we're building huge amounts of memory, and the cost is a big deal, clearly. But maybe that mindset also needs to change going into the future, because this is assuming that memory is just a slave device that just serves a compute master, right? Maybe that needs to change. Okay, so if there's some interesting that happens now. Now the row buffer has the row in the sense amplifiers, because row buffer is sense amplifiers, right? Now if the memory controller wants to access row 0 and column 1, it knows that it activated row 0, so it just needs to send the column address. It's called the row buffer hit. This is a very simple cache. We're going to see caches in the next lecture, but this is a very simple cache at the DRAM level. If the memory controller knows that row 0 is already open over here, it doesn't activate the row, so it doesn't send the row address, it just sends the column address, 1, and then the DRAM chip sends back the column that the memory controller asked for through the multiplexer. Okay, so you have some level of caching that's already integrated into the DRAM. It could be 8 kilobytes or 16 kilobytes. Okay, now let's say if the memory controller wants to access row 0, column 85, again, it's a cache hit or row buffer hit, and it just sends the column address, and the DRAM chip sends the data out. Okay, now if the memory controller needs to access some other row, let's say row 1, now it realizes that this row buffer contains row 0. It first needs to close the row. This is called a row buffer conflict. So there's a conflict in the cache. We're going to see this a lot more in the next lectures. And the memory controller needs to close the row. At a high level, this is writing data back into the array, but it's called a pre-charge operation in DRAM, prepare the array for the next access. And it supplies row address 1 to DRAM, and the DRAM chip activates the row. It takes time, of course, and then the memory controller supplies the column address, and the memory chip sends column 0 from row 1 in this next case, right? Okay, so again, this is an abstraction, right? But this is a good abstraction to work with. Now, I said that this is the bank and this is the lowest array that we're dealing with, and that's a lie. Internally, so I also said that this is, like, let's say you have 32,000 rows versus, I don't know, it could be 16,000 columns. Even this is too big. What does too big mean? Too big to operate reliably at the latency levels we want. Because the interconnects are huge. Basically, imagine an interconnect going through 32,000 bit cells. Right? That's what's happening here. Because this is too big internally, people divide this into what's called subbanks or subarrays. So this is your bank, 32,000 rows, as I said. Internally, you actually divide this into many subarrays, each of which may have, let's say, 512 rows or 1,024 rows. And what you do is you really do the sensing locally over here, and then bring the data outside afterwards when you send the column command. So what this enables is really to reduce latency. Instead of the data going through a huge interconnect, huge wire, it goes through a smaller wire. And that's really the state of the art today. But even this is an abstraction. So internally, you see even more arrays, right? So this is the subarray that I showed you. Another picture. If you're really interested, you should actually look at these papers that covers. It's very hard to find easily accessible material on how DRAM works. DRAM manufacturers make it really hard, let's say, to make it easily accessible. But if you read some of these papers, you'll find them much more easily understand. But basically, this is a subarray. This is a bank. So essentially, you can think of the bank this way. We divide into subarrays, but not only subarrays, but also mats. So each subarray actually consists of some arrays internally also, a vector of arrays, basically. And the reason is, again, it takes time to access the word line, activate the word line, as well as get the data out of the bit line. And we want to minimize the interconnects as much as possible. Okay, without going into a lot of circuit level detail, that's essentially, it's a hierarchy of arrays that we have built from the top down. as well as I showed you bottom up a little bit as well. So if you really want to know more, this picture is actually from this chapter that we had written with one of my prior PhD students, Vivek Seshadri, who's now at Microsoft Research India. And if you really want to get a good understanding of DRAM, see section 2 of this one. Okay, now let's take a look at how a processor transfers a cache block, right? That's also important because you want to transfer a cache block from memory. A 64-byte cache block gets mapped to a single rank, essentially, because you can only access one rank at a time. You cannot access ranks concurrently in the same channel. So how does that cache block get mapped? So what happens is part of the cache block gets mapped to row 0, column 0 over here, let's say. And in one cycle, you transfer 64 bits of it. So a 64-byte cache block gets transferred in 8 cycles, 8 memory cycles. First, you transfer 64 bits from this rank. Each chip supplies row 0, column 0. And each chip supplies 8 bits, as you can see. So I get 64 bits out of the first 64 bits of my cache block. That's the first cycle. In the next cycle, I get row 0, column 1. Next 64 bits of my cache block. Again, 8 chips are involved, as you can see. In the next cycle, I get row 0, column 2. Next cycle, row 0, column 3, until row 0, column 7. Right. So basically, that's how it works today. Because the interfaces are small, they're not as wide as 64 bytes. You get 64 bits at a time from the memory chip into the processor. And this is really the cause of the latency and energy base. All of these accesses take time and also energy. These interconnects, I mean, these look very, let's say, innocent, right? These red things over here, they're not that innocent. They're basically consuming a lot of energy. That's 6,400 times in addition. It's consumed by this stuff mainly. It's the interconnect between the processor and memory chip. These are huge energy-hungry interconnects. It's not just interconnects, it's what you do to drive those interconnects also, right? DRAM chip needs to put a lot of energy to drive the interconnects out. Okay, so that's the cause of the energy and performance as well. Okay, let's talk about memory technology a little bit more. I've given you, so okay, this was an array structure, right? I picked DRAM as an example. If you look at flash memory, it looks similar. There are some differences in operation, but it's similar in the general mentality, hierarchical array organization. SRAM, it's similar again in the general mentality of hierarchical array organization. All of these concepts still apply. The row buffers may be different in all of them because the technology is different, right? So let's take a look at technology a little bit. So this is the DRAM technology. It's called dynamic random access memory. You've seen it before. We talked about refresh in earlier lectures, right? So capacitor charge state indicates the stored value. This is our capacitor. Whether the capacitor is charged or discharged indicates storage of 1 or 0, depending on your encoding. So you only need one capacitor really for storage. It can be very simple, very cheap. But you also need the access transistor clearly so that you can figure out the value of that capacitor, right? Whether there's charge or not, no charge. So this access transistor adds more area. So unfortunately, as we discussed, capacitor leaks through the resistance capacitance path, RC path. So over time, you lose the charge in the capacitor. And as a result, it needs to be refreshed, as we discussed. And this is a big problem with DRAM. So this doesn't exist in SRAM technology, for example. SRAM technology doesn't leak. I mean, there's leakage, but because of it actually doesn't lose the charge because it also has this, let's say, feedback loop, as we will see, as we have seen also actually. So this is all of our memories are built with. Every one of you have computers with memory, and the external memory is all DRAM basically. This is a huge market today. Now it may change, who knows. Static RAM, all of our caches are built based on this, as I said. It's true cross-coupled inverters. You've seen this before. We've seen it actually in lecture 6. This feedback path enables a stored value to basically persist in the cell. Persist meaning that while the cell is powered on, because of leakage, you don't lose the value. If it's powered off, all bets are off because it's not non-volatile. It's not made of some material that's non-volatile. So I etch something in stone, for example. I would assume it's non-volatile, right? Unless somebody goes and does something to that stone, that whatever I etched will stay there for some time. This is not true for SRAM, but it's true for SSDs. The material over there doesn't get lost. Well, of course, it depends on how long of a time dimension you're examining, right? Millions of years? I don't know. right? But tens of years, it may be okay. Okay, basically you get 4 transistors for storage because each inverter has 2 transistors, as you remember, hopefully, but 2 transistors for access. So these are the access transistors over here. And you can see that you have the bit line and bit line bar because you can actually tap into 2 parts of this feedback loop. One is the value and the value bar. And then you can build a sense amplifier that basically senses the difference. It's called a differential sense amplifier, which can be much faster than sensing only one of these bit lines. That's the idea. So this is one of the reasons why this could be built fast. Capacitor leak. So the sense amplification of the capacitor is actually takes much longer. The fundamental technology here is the capacitor. Here, the fundamental technology is the transistor, as you can see. That's what stores the charge. And capacitor is fundamentally slower. That's why DRAM is slower. And this is clearly more faster, but more expensive. Okay. So memory bank organization is actually very similar in many memory technologies. You have a, I'm going to go through this quickly because we've seen it in DRAM. But independent of the technology, you have a 2-dimensional storage array. You need to give the address. And most significant bits specify the row. You decode the row address. You activate the word line. You get the entire column. And then with the least significant bits of the address, you select which bits you really want out of this array. So if you want this red portion, you still need to activate the entire row and then multiplex out the red portion. I'm not showing you the row buffer over here, but row buffers may exist as well, right, in many technologies. So I've already said this basically, so I'll go through this quickly. Yeah, this is for your benefit, basically. And then if you really want to access some other row, you need to pre-charge the bit lines. This means that preparing the array for next access. To really know what's going on underneath, you'll need to take a next level course because we don't have time to cover what happens with the pre-charge, right? This again very much depends on the technology, but it prepares the array for the next access so that you can sense the next row that you want to access. Okay, so if you look at static random access memory, the fundamental storage element is this, but internally the bit cell array looks like this, right? And you supply an n plus m bit address, and essentially we already discussed how each cell operates. You do it at the array level. You activate one word line, and you multiplex out some number of bits depending on how many bits is the interface of the SRAM. So you decode the address, you drive the row enable signal or word line. Selected bit cells drive the bit line, so you read the entire row. And then there's some differential sensing and column select. So you need to select the column that is being accessed and pre-charge all bit lines for the next access. So access latency is dominated by word line driving and also bit line sensing, if you will. And that's why arrays are actually, people try to make these arrays as rectangular as possible so that the interconnects are balanced on both X and Y dimensions. Okay, so you can read more, but you hopefully get the gist of it. It's essentially very similar in DRAM, except the cells look like this, right? So essentially, read sequence is very similar to SRAM. You activate the word line. You supply the address. You activate the word line. The bit lines get driven, and then you do the sensing. Sensing is a bit different, clearly, because it's a different technology. And then you have a multiplexer after the sensing. And then you need to pre-charge all the bit lines. So as I said, the difference, the DRAM chip gets addresses, the row addresses and the column addresses separately to save pins. Whereas here we showed that in SRAM, we showed that you could actually get both addresses at the same time because SRAM is usually on chip. You don't have pin constraints. Okay, and also the big difference is reads are destructive, meaning whenever you read a cell, you need to amplify and restore the charge back, and you get charge loss over time. And so you need to refresh, basically. And you're no stranger to refresh because we discussed it early on in the lectures. So there's a memory controller that needs to read each row and amplify it and write it back every so often, every 64 milliseconds, for example. Today, it could be every 16 milliseconds at high temperatures. So it's becoming actually worse, as we discussed also earlier. So refer to lecture, I think, two for that. Okay, so basically, there are trade-offs between technologies. I'll give you one example from DRAM and SRAM. Clearly, DRAM is slower access because it has a capacitor. SRAM is faster access because there's no capacitor. It's all transistor-based. And capacitor is fundamentally harder to sense. Let's see. DRAM is higher density because it's actually very simple, whereas SRAM requires 6 transistors. DRAM is lower cost because it's higher density. SRAM is higher cost because cost is usually dominated by how many bits per millimeter square you can have. If the bits per millimeter square you can have is high, then cost is usually low. Okay, the downside is DRAM requires refresh. Refresh requires extra circuitry, extra power, extra performance periodically. SRAM doesn't require refresh. That's the good part. And DRAM requires a special manufacturing process. That's why we do not put DRAM on our chips. Why? Because capacitor is actually very different manufacturing process compared to logic, CMOS logic today. And that's why there are companies that specialize in this one. Logic companies are usually specializing in logic and not the capacitor manufacturing. And in SRAM, because everything is made of transistors, CMOS logic, essentially manufacturing is compatible with the logic process. That's why we have SRAM as our, let's say, caches, right? Or register files can be SRAM as well. So you can see that the differences also dictate how the businesses have evolved. Yeah. Interestingly, one of the most advanced logic companies today, Intel, used to manufacture DRAM, but they made the decision to get out of DRAM business. The first DRAM was manufactured by Intel in 1971. And then they did not manufacture DRAM for quite a while. Now other companies are manufacturing DRAM. Let me give you an aside, because this is not just, there are some future memory technologies that may exist also. I mentioned this briefly in one of the earlier lectures, the first lecture, I think. But phase change memory is interesting. This is actually something people have been working on. Technologies change over time. And a phase change memory works in a very different way. Basically, it has this phase change material. Chalcogenide glass is one example. There may be other materials. This material exists in two states in nature. One is amorphous and the other is crystalline. And you can basically change the phase of this material by heating and cooling very carefully. You need to heat it up to, for example, 600 degrees Celsius to change the state sometimes. Now, the fact is that these two states have different resistivities. So one state is very high resistance, one state is very low resistance, and you can change the state and predictably encode one state as 0 and the other state as 1, for example. Now, interestingly, amorphous state has low optical reflexivity and high electrical resistivity, and crystalline state has exactly the opposite. This technology was used in rewritable CDs, and rewritable CDs use a mechanical sensing process. By shining light, they would determine the reflexivity of the cell, and that reflexivity determines whether the cell has 1 or 0, right? So that's one way of reading, extremely slow. More recently, people have actually figured out how to read these cells extremely fast by building sense amplifiers like DRAM or SRAM, specialized for phase change memory, of course. Building sense amplifiers integrate into logic, essentially. As a result, this technology became extremely interesting, right? So this is based on our paper, actually. We were envisioning how should memory evolve. This picture was drawn in 2007. And we were thinking, okay, DRAM is not doing very well because there are so many reliability issues, etc. Over time, we should put phase change memory in our systems. And maybe over longer time, I don't know, 20, 30 years later, you would have phase change memory in the system that's much more scalable. If you really want to understand this, you can take a look at the papers. And this is the paper we wrote, actually. I mentioned this earlier. And if you're really interested in phase change memory, I'm not going to talk a lot more about it. You can find it in this paper. Okay, and this is a shorter version of the paper. Now, the nice thing is this paper was actually, I was in the US last week, and this paper was awarded one of the Test of Time awards in the non-volatile memory symposium in 2022. Okay, so basically at that time, we were dealing with nothing. We were basically imagining, right? But the good thing is, imagination is the beginning of how things change. And Intel actually introduced this technology in 2019. So you can buy these chips, and they're actually high density, as you can see. They're much higher density than DRAM. So let's take a look at the trade-off space. I think it's important to do this. But DRAM is faster access, it's capacitor-based. PCM is slower access because you have heating and cooling based on phase change operation. DRAM is lower density now compared to this. Capacitor is less scalable, it's higher cost. PCM is higher density. Phase change material is actually much more scalable. DRAM requires refresh. There's no need for refresh in phase change memory. There may be other issues, but no refresh. DRAM manufacturing, not so great. PCM manufacturing, not so great. Less conventional processes, basically, less mature. So over time, this may mature. Right? There's also that over time aspect. DRAM is volatile. Phase change memory is non-volatile. So there's some characteristics that are really interesting. Phase change memory can replace your SSD also, not just DRAM. Right? DRAM, fortunately, DRAM has no endurance problems. Unfortunately, phase change memory has endurance problems. What does this mean? when you write to memory like 10 to the 8 times, you cannot do anything to that memory cell. So don't write to it too much. So it's great for reading a lot, but writing, okay. So this is again technology dependent, very much technology dependent. DRAM has lower access energy. Unfortunately, the PCM has higher access energy. So it's a trade-off space basically. This can be very high capacity, but it has other issues. And the fundamental difference is actually today's memory technologies that have been extremely successful are charge memories, DRAM and flash. We're very good at figuring out how to do these. We still need to learn how to do these emerging technologies, phase change memory, STT-MRAM, memristors you may have heard of, which I don't really have time to go over. And these are actually very, very interesting. So phase change memory you talked about, for example, but there are magnetic memories where the state is encoded based on the polarity of a magnet. Whether the magnet is facing this way or this way, that is basically your state. It could be your 1 or 0. Sometimes you change the atomic structure of the material, and the difference in the atomic structure dictates whether you have a 0 or 1. Resistivity, basically. So these are fascinating technologies, and they can actually make their way up into our memory systems. Okay, I don't have time to talk more about it, but you can find a lot of lectures on these topics online. Now let me talk about one more memory, and then we're going to be done. So flash memory, as I said, this was an emerging technology 20 years ago. Today, every one of us, I believe, well, everyone may be an overstatement. I'm sure there's someone who doesn't have something like this, but every one of us have flash memory in our hands, right? So that's how technology changes lives. And I believe this is, maybe you don't have it in your hand right now, but you may have it soon. You'll have it in your laptop. This has flash memory. I don't imagine carrying this laptop around without flash memory, basically. Okay, if you want to learn about flash memory, there's a lot also, and you can take a look at these lectures and also courses as well. Okay, I'm done. I think maybe we'll cover this later on in one of those lectures. I'll see you tomorrow when we start the memory hierarchy and caches. Take care. Sure.
First of all, just about DRAM.
Okay.
I've heard the term memory leak. Is that exactly when DRAM loses?
Charge. No, it's not. Usually, let me take this off. Memory leak usually refers to a software issue where you don't deallocate memory. Yeah, unfortunately, they're both called leak. So but it's usually, if I hear the term memory leak, I would say it's really a software issue where you forget to deallocate memory, for example. Oh. Yeah. Okay, let me put this over here. I'm coming. Okay.
Yeah, I sent that one.
Yeah, but
it wasn't. I thought it wasn't.
okay, yeah, that's good.